Section 1. A new spin on power, introducing supercritical turbines. Supercritical turbines are a new kind of machine that can make power in a much better way. They use a special fluid heated and pressurized above its critical point. For carbon dioxide, above 31 degrees centigrade and 74 bar, the fluid is in a unique state called supercritical. It is not quite a liquid, not quite a gas, it has properties of both. Very dense like a liquid, yet it flows easily like a gas, transferring heat exceptionally well. When CO2 is in this state, we call it supercritical CO2, or SCO2. For over a century, steam turbines powered the world, but with big footprints and water needs. Traditional plants are massive and lose a lot of energy as waste heat. Supercritical turbines offer more electricity from the same heat, in much smaller packages. Closed-loop SCO2 can run with minimal water, ideal for dry regions. Cleaner, more flexible grids with lower emissions, SCO2 technology aligns perfectly with these goals. This simple idea could change how we generate electricity. The Brayton cycle, how supercritical CO2 turbines work. An SCO2 turbine operates on a simple, elegant closed loop where the same fluid cycles continuously. Think of it as a circle of energy conversion: compress, heat, expand to make power, then cool and repeat. The cycle has a few clear steps. First, cool. High-density SCO2 is compressed. Because it behaves almost like a liquid, this takes surprisingly little energy, a key advantage. Next, the pressurized SCO2 is heated in a compact heat exchanger by an external source like solar thermal, industrial waste heat, or a reactor. Hot and at high pressure, the fluid now holds tremendous energy. It rushes through turbine blades and expands, spinning the rotor at very high speed. That rotation turns a generator to produce electricity. Crucially, the SCO2 remains in a single supercritical phase. There is no boiling or condensation. After the turbine, the fluid is cooler and at lower pressure. A cooler removes excess heat. The fluid returns dense and cool to the compressor, and the cycle repeats continuously. By avoiding phase changes, Brayton sidesteps large latent heat losses that steam Rankine cycles must endure. It is a more direct path from heat to electricity. The result is a simpler, more compact and more efficient power system. That is basically how it works. Section 3. More power from less heat, the efficiency advantage. Older coal and gas steam plants convert about 30 to 40% of heat to electricity. SCO2 cycles target 50% or more. In many plants, only 1 out of 3 units of heat becomes electricity, the rest is wasted. SCO2 is dense, enabling exceptional heat transfer in small heat exchangers. A 10-point efficiency jump from 40% to 50% can cut fuel use and CO2 emissions by roughly 25% for the same output. Less fuel means lower operating costs, savings that add up to millions over a plant's life. Because SCO2 compresses like a liquid, compressor power is smaller, reducing parasitic load and boosting net output. It is like an engine that uses less of its own power just to run, leaving more to move the car forward. That is the efficiency advantage in a nutshell: cleaner and more affordable power, higher efficiency, lower fuel, lower emissions. Beyond efficiency, the second revolutionary feature of SCO2 turbines is their incredibly small size. Steam plants are huge because low-density steam demands enormous turbines, pipes, and heat exchangers. That footprint makes them expensive, difficult to site, and slow to build. SCO2 is hundreds of times denser than steam, carrying the same energy in a tiny fraction of the volume. A 10-megawatt steam turbine can be the size of a bus. An SCO2 turbine for the same output might fit in a small room. Compact size enables modular construction, factory-built power blocks, standardized for quality and speed. Modules ship by truck or rail and assemble quickly on site, faster, safer, and cheaper. Scale up by adding modules, or deploy a single 5 to 10 megawatt unit for remote communities, bases, or disaster response. Producing power close to use improves energy security and enables waste heat capture. This shift favors resilient, decentralized, and responsive power networks over monolithic plants. The beauty of the SCO2 cycle: it is heat agnostic. It converts thermal energy from many sources: solar, industrial exhaust, nuclear, geothermal. In concentrated solar, mirrors focus sunlight to create high-grade heat that can efficiently drive SCO2. Next-gen reactors run hotter. SCO2 thrives at higher temperatures, boosting plant efficiency. Heavy industry expels vast hot exhaust. SCO2 turns that waste heat into electricity without extra fuel or water. Paired with thermal storage, daytime heat runs turbines at night, making renewables more dispatchable. A shared SCO2 platform can raise efficiency and cut emissions across the energy system. For years it was lab work and simulations. Now SCO2 is leaping into the real world. A 10-megawatt test loop in Texas has run a full SCO2 cycle, hitting over 27,000 RPM and proving integrated stability. A commercial SCO2 unit at a steel plant captures approximately 700 degrees centigrade exhaust to make power, with no extra fuel and minimal water. These pilots refine materials, controls, and startup shutdown strategies, building confidence for scale-up. It is becoming a practical tool for cleaner, more efficient power. Operating at 200+ atmospheres and up to 700 degrees centigrade pushes materials, seals, and bearings to their limits. Near the critical point, small temperature or pressure shifts change density fast. Advanced model-based controls, often AI-assisted, keep systems stable. Meticulous design, safety protocols, and trained operators are essential as deployments grow. In summary, supercritical turbines offer a simpler, smarter path from heat to electricity, efficient, compact, and flexible, a cornerstone for a resilient, sustainable grid.